You can see the tidal spectral portraits and the eigenvalue dynamics of non-self-adjoint Sturm-Liouville will operators with small parameters. And
thanks for introduction. Well, I will speak about spectral problems of non-self-adjoint Sturm-Liouville operator. And first I'd like to say where these problems do appear. First of all, it appears in hidden dynamics. There is the so-called celebrated Orson-Lefeld equation. It looks much more difficult than Sturm-Liouville. However, in some sense, it can be reduced to Sturm-Liouville problem, certainly with some accuracy. Excuse me, I did not think that the talk will continue only 30 minutes, so I will skip some pages. So there is a reduction which allows to come to a model problem, and model problem is this one, Sturm-Liouville with potential Q, and for simplicity we consider Dirichlet conditions. This problem is not non-standard because of this imaginary number I. If we omit, if we cancel I, then we will have usual quasi-classical problems. You see epsilon equals h, it's a Planck constant, and there are plenty of works where eigenvalue dynamics is investigated for such kind of problems. But if you put here I, the situation changes dramatically. You see, if you consider the simplex case Q of x equals x, then the spectrum here is misprint epsilon minus 2. So if epsilon is small enough, then the picture, this is real calculation. The spectrum is located on the imaginary axis and on the segments which are from -1 to -I over square root 3, and symmetrically from the right side. For Orson-Lefeld problem, I told you that approximately Orson-Lefeld problem, the spectrum behaves like in the model problem. The segment is becomes like that, but the distance between these lines is 1 over epsilon square, logarithm epsilon. So model problem really approximates much more complicated Orson-Lefeld. This is for Q flow for Q of x equals x squared. This is Orson-Lefeld problem for Q flow problem. You see from the right you have not very clear location, but if you make epsilon smaller and smaller, then it becomes almost one line. That's for Poisson flow And I will skip investigation in this area. I'd like to say only that I do believe at least in 1997 I proved rigorously because actually a lot of works were with computer calculation, but I succeeded to prove that really the spectrum concentrates for Q of x equals x really concentrates to these segments and to this imaginary line, and the zeros coincide with the eigenvalues coincide with the zeros of IV functions. Decay are zeros of the IV function which are located on the negative axis. But approximately 20 years ago, I wrote some another papers with my students for Creator, for Poiseuille flow. But recently, my interest again, I came again to this problem, and we did obtain some much more general results. So I will not put the number I in this problem like it was before. I cancel here I, but instead of Q of x minus lambda y, I will consider the function Q of x lambda, any complex function which is polynomial on x and analytic in lambda in some domain G, in domain D, in the complex plane. And we will discover some phenomena which are interesting even for Q of x equals Q minus lambda when Q is real potential. So we will obtain something new even in the case which is well investigated in the classical case when epsilon is Planck constant. Certainly, generalization when Q is polynomial or analytic function on lambda is quite important because we frequently meet a lot of problems which are nonlinear in lambda. It's not a big surprise. So before I formulate the main results, I have to introduce some notations and definitions. Certainly, to understand everything which is happening here, one has to learn the things from Stokes graph theory. I remind, we first define these action integrals, take Cj any root of any zero of function q, and consider this in C plane, consider this action integral. Then this is not this is a multivariate function, but if we consider harmonic functions real as Sj equals to 0, then you have for simple, if Cj is simple, then you have something like that. Certainly for harmonic function, real Sj equals to 0, they define cubes in complex plane. And these cubes look like that. The angle is 2 pi over 3 between each cube. If you have Cj and Ck, then Stokes complex will behave like that. And the union of all Stokes complexes is called the Stokes graph. Then I have to define some functions which are very important in the signal. This function Sj of lambda, and this function Cj integration from the point from 0 Cj of lambda to the point A. We consider our problem first on the we consider our problem on the segment AB, and the action integral taken from A to Cj can be continued as analytic function on lambda, as well as in the case Sjk. And the next definition is the following. Again, we take real part of, excuse me, we have to define also B of lambda A is the action integral from A to B. And now it's not easy to explain. First, let me formulate the following result, and then I will explain a little bit more. Consider all the cubes in lambda, not in C plane, but in lambda plane, real B of lambda AB equals to 0, real Sj of lambda A equal to 0, the same of lambda b equals to 0, and real lambda, real s j k of lambda equals to 0. This is harmonic function, so these equations define curves in the lambda complex domain. The result is the following: that the limit spectral graph, I mean the spectrum, as epsilon tends to 0, the spectrum of the problems is a subset of all these cubes in the lambda plane. It is a subset of all cubes in the lambda plane. However, these could, what is the subset? How to describe this subspace precisely? In this case, we have to define the so-called essential balanced cubes, essential critical cubes, and essential singular cubes. These cubes I call singular. These cubes I call critical, and these cubes I call balanced cubes. And I have a rule how to distinguish essential cubes from non-essential. It's unfortunately I have not. I will explain only for q of x equals x. Stokes graph in this case are very simple. You see, if you critical lines from -1, all this line, from 1 to all this line, balance cube, this imaginary axis, and essential parts are only from -1 to this point B, from 1 to B, and from B to -infinity. So there is an algorithm which allows precisely describe the limit spectral graph which this is the spectrum is located when epsilon tends to 0. This is for x squared. You see much more difficult in this case. This is critical. This is singular line from -1 singular line. This is critical lines. This is critical lines, and this is balanced cube. And you see only some parts do participate in do create cubes in the limit spectral graph. Not all of them. This is the picture how to select these essential cubes. And quantization formulas. Unfortunately, I have not too much time to explain what's going on, but you see, when epsilon tends to 0, you have eigenvalues concentrate more and more densely. They become closer. And it is epsilon -1 is a characterization of how close they become. Actually, you see the formulas, these formulas, if Q is real, these formulas are well known. This is the so-called Born-Zimmerfeld quantization formulas, and they actually they equivalent to the value formula for eigenvalue. because I can claim these assertions not in the form of Borzone field. I can claim this in the form of wave. So the number of eigenvalues on the cube, on the critical cube, for example, is equal to this one, approximately, up to this accuracy as square root of epsilon. This is how to obtain these quantization formulas. Actually, we use it's quite non-trivial task how to prove these quantization formulas, but unfortunately there are some studies in Stokes graph theory which allows to do those, and there are so-called transition matrices, but it's not a simple problem because we have to apply transition matrices several times to obtain a necessary equation. Certainly not for all functions we can calculate everything, but for some functions, it's like this one, one can do this completely. And the other thing which I wanted to say, I have quite not too much time. But 5 minutes time, yes. And here I will turn the studies of PT symmetric operators is quite popular last time, and there are plenty of works. And one of the main problem is the following. When the spectrum of a PT symmetric operator, so let me write like this, minus plus I cube of x, y equals lambda y. Let me q be even function, real even function. Then you see here I, and certain problem is non-self-adjoint. But it's surprising that sometimes the spectrum of this problem is real, and moreover, the operator is similar to a self-adjoint operator. And one of the main problems is the so-called non-self-adjoint quantum mechanics is to find conditions when the operator, which is non-self-adjoint, which is symmetric, really has only a real spectrum, and when it is similar to the self-adjoint operator. I told already that there are many investigations, just for particular operators, but all these investigations are only on the whole line. It turns out that the case of the whole line is really the simplest one, because in the limit spectral graph, in the case of the whole line, consists only singular lines, no critical lines, no balanced cubes. Finite interval or semi-finite is much more difficult. For example, even formulas which we obtain for the final interval, even in self-adjoint case, they are new. They are new, even in self-adjoint case. So, theory which we can prove the following. If Q, let it be P, is small enough. I mean, if epsilon is less than these numbers, P infinity, P1, P2, this is norms of P in infinity, L1 and L2 spaces. We can guarantee that in this case, operator A has only real spectrum, and it is similar to self-adjoint operator. When epsilon is greater than these numbers, everything may happen. Everything may happen. And it is quite important to find explicit number epsilon when operator becomes non-self-adjoint. And it turns out that we can do this for, at least now, we can do this only for E of x equals x. And it is quite difficult work. Theorem, first theorem which I demonstrated above, gave epsilon equals 3 and 7, approximately. 3 and 7, which guarantees the self-adjointness. But in case, for the case Ix, but actually epsilon is 12 and 6. And it turns out that it can be done in terms of special functions, u plus and u minus. We can point out explicitly the numbers when the eigenvalues collide and they come to the complex point. Thank you very much. That's it.
We have time for some remarks or questions.
This topic, I suspect, is quite new for this audience, but but believe me, last time appear more and more papers from specialists in operator theory, and the topic is not exhausted. There are plenty of problems which one has to clear up.
If there are no questions, then we'll thank again the speaker. No, we have started a little bit earlier. Yeah, it's already.